Good morning from Kyiv, Ukraine. It is a beautiful autumn day. I have to admit, it's a little bit cold. That is why I'm putting my jacket. I guess you recognize the landscape, the Dnieper River behind me, Volodymyr the Great statue, considered, let's say, one of the founding fathers of Ukraine, even though the history is not that straightforward and simple. But here I am in the country of Ukraine to teach you something that has made Ukraine so famous. What is the thing? Well, a little bit of history. On April 26, 1986, something happened in Ukraine that made it the most famous country when it comes to nuclear activity. You guessed it, I'm referring to the incident or the disaster of Chernobyl. That is why I came to Ukraine to teach you from the land that has become quite famous for nuclear reaction, how electricity is produced from the source, the power plant, transported on hundreds, probably thousands of kilometers until you, the consumer, in your house, so you could enjoy your favorite YouTube video like this one, and so you could click on the like button. Thank you very much. All right, the police just came, the police of Kyiv. They thought like I'm building some products or selling some products, otherwise I can't do it. I said no, it's just for my YouTube videos. They said okay, that's fine. But somehow it's product also, no? Anyway, if you are ready, I'm very ready. Let's start from you, the consumer. So this is your house, and we'll be using the European standards of electricity. So we are talking about 230 volt AC, 50 hertz. This is the power that the house will consume. So if I say here these are the electric cables. They go to something which we call transformer. So this transformer will even step up the electricity to a higher level, and we'll see why. So let's say from here I go. So this is the support that transports electricity, and I will do something like this from here. So we are getting closer to the power plant where electricity is produced. The thing is that since this is a long distance, as you know, tell me if I'm wrong, but most of the houses, they are way far from the power plant. So the distance here is really long. It goes on many 100 kilometers. Therefore, the level of voltage here is 400 kilovolt. It could be also 230 kilovolt, depending on the distances. But let's take the highest one, 400 kilovolt, 50 hertz. Okay. So why do we elevate the voltage to 400 kilovolts? Why don't we simply put it here at 230 volts and transport it to the houses? Why we bother increase the level of voltage to later on lower it back to a smaller level of voltage that you can use in your house in a safe manner? We'll have the answer to that later on in a dedicated video where we will explain the relation between the voltage, the power, and it will make more sense to you. But for now, let's try to have a bigger picture that will help us understand where electricity comes from its source through all these hundreds of kilometers until it's delivered to our house. Your house is here. I said you will have different level of voltage. Let's say here you are at 230 volts, which is more the level of your house, and then before that you will elevate from 230 to 90 kilovolts in a smaller substation, then from 90 kilovolt to even 400 kilovolt. So there is many level of elevation and like stepping up, stepping down the level of voltage. Just for simplicity, I'm just drawing to you a transformer here. You will have at least one transformer, in fact many, that will step up, step down the level of voltage, and then up. Think of this like these cables are going on very long distances, let's say 500 kilometers for example, and then we'll get closer to the power plant. And here is the power plant. The power plant will not produce electricity at 400 kilovolt, but way lower than that. If my memories are correct, it's about 15 kilovolt. I will not draw a direct link between the transmission tower and the power plant. Let's go directly. I'm impatient to discover the power plant itself. So the output of the power plant, as we said, will be a lower voltage, 15 kilovolts. But don't care about the things in the middle. What will produce electricity, by now I think you guessed it, is an electric machine. Call it motor, but it's a machine. It's an electric machine that can operate either as a motor or as a generator. In this case, we will use the electric machine to operate as a generator because we want it to generate electricity. So it's going to be something called generator. The generator will convert mechanical energy to electrical energy. Therefore, there needs to be someone who turns that generator. That someone is called a turbine. So here is the axis, the rotor of the generator, and it's connected to something that is called a turbine. So the turbine is connected directly to the generator. If it turns, the generator turns and produces electricity. Now the question is, who will make this turbine turn? You see the pipe that is coming from the top will bring very hot steam. So the steam will come at a certain speed, will go down like this, will drop on the turbine, and then the turbine will turn. That steam need to be cooled down so it can comes back to a liquid form, which is water. It will condensate here, so therefore we already know that this part here will be blue. So this will be blue because this is water. The steam coming from the top will condensate and forms water. We will see how it will condensate. It's not a natural process. Someone needs to cool that steam coming down so that we can form water and send it back to the circuit that gave us steam. So for this water to come back, to go back somewhere else, we need a pump. Put the drawing here of the pump. We go like this. So this is water. This I'll draw it in yellow color and I would say it's steam. Okay? So this is steam coming here. Again, this steam is very fast. It will come at a certain speed, rotate the turbine rotates the generator. Since the generator, the rotor of it is not made of permanent magnet, but it's an excitation, an exciter circuit that creates a magnetic field. A magnetic field in the rotor, if I turn it, I create electricity. It is by the law of Lenz-Faraday that says that the voltage is equal to the variation of the flux on the time. If I vary the flux of the rotor by turning the turbine, I create voltage. If I create voltage, I'm producing electricity to people. So let's continue with this pipe. Alright, so this is normally it's at the same level, okay? But just to make the circuit make sense. So we know that here we have water coming here, right? But somehow by some magic process, we get steam. What's the name of this one? Here, it takes water from its liquid state to a gas state. So it takes water, transform it to steam. Therefore, this one is called a steam generator. Simple word, right? This one, we said it's turbine. We are still missing something here because steam does not go into water. I mean, yes, it will with the time cool down and becomes water. But here we cannot wait. We gotta make it become water. So there is something missing here. I'll show it to you later. This steam generator will transform water into steam. It will change the state of water from liquid state to a gas state. If you want this process to happen, you need a source of energy. And that's where the nuclear reaction comes into play. In fact, it could be anything. It could be burning coal. It could be burning gas. It could be doing anything that creates energy, heat, something that will help us transform water to steam. From here to here, don't care about the source of energy. Is it a nuclear power plant? Is it a coal power plant? We don't care. We just need someone who will warm this water, transform it into steam, so that we have a steam coming at a high speed that will turn the turbine, turn the generator, produce electricity that will go into our houses. But in our cases, we choose nuclear reaction. There are many reasons why. That is actually what you will see in the next video, why we choose nuclear reaction over coal, over any other source of energy. Some people love it, some people hate it, some people are afraid of it. I'm in a country where, surprisingly, I would expect people to be afraid of nuclear reaction, of nuclear power plant, but they still support the idea of having civil nuclear power for reasons that are more political. They don't want to depend on their neighboring country, Russia, to get their gas or coal, for example. So to them, having a nuclear power plant will help them be more independent from their neighbor when it comes to a source of energy. So back to our topic. We have a steam generator. This is closed, right? Who will warm this water? Our source of energy, since I came to Ukraine, a country that is famous for its nuclear activities, our source of energy is a nuclear reactor. We will use a nuclear reactor that does the nuclear fission, and since the atoms will split, the uranium atom will split, they will release energy in forms of heat. That heat released when we split the nuclear atom will be used to boil this water, transform it into steam. So this is how we will do it. So red color because it's hot, in fact very hot, more than 280 degrees. If I remember well, it was 285 degrees. So a water that is at 285 degrees. Nothing shocks you here? Didn't we say that water evaporates at 100 degrees C? So how comes in this case we have water that is still liquid at 285 degrees C? I let you think of it until I finish this drawing. So now we have our source of heat. This one will heat the water. This one is called nuclear reactor. You are wondering where the uranium fission happens. It happens exactly here. And this circuit that you see is what we call the primary circuit. And I will show you the building where it happens. So this reactor here has these blue lines. You are wondering what are these blue lines? These are the control rods. Why we call them control rods? Because someone needs to control what we call the nuclear fission, the reaction in chain, because when a uranium atom splits, release 2 or 3 neutrons. These neutrons will go hit other uranium atoms, they will also split. So if you do nothing, it's a reaction in chain, and each single atom releases 2 to 3. So if you do nothing, you will end up with something that is uncontrollable. A lot of neutrons hitting other atoms, splitting other atoms. You don't want to have that. You want to have someone that controls that reaction. To do so, you need these control rods made of borons. They will absorb that neutron, because what makes the atom split is these neutron, right? These control rods, the blue lines you see here, these are the guys that will absorb the neutrons. But more on that in a separate video that I will dedicate just to the nuclear reactor, so you could see how things are happening inside, like closer in the nuclear reactor. We'll also see the different type of nuclear reactors. Of course, the most famous one is what we call PWR, which is pressurized water reactor. That is the most famous one, the one that is reliable, using what we call thermal neutrons. These are the slow neutrons, because you have also the fast reactors using fast neutrons. The most common one is the PWR. It is also the most common one in the country where I come from, the country that is championing the nuclear fission. More than 70% by electricity consumed in France comes from nuclear power. It is the #1 country in the world with this percentage. Therefore, in France we use PWR, pressurized water reactors. These are the ones that we will focus on. There is something very important we need to see here. Let's first finish this one. So now that we have our source of heat, the thing we were looking for to warm this water, transform it into steam, so that the steam can go at a certain speed, turn the turbine, turn the generator, produce electricity. Now that we have this source of heat, which is liquid water, this is liquid water that is very hot. It's in fact at 285 degrees C, and it's liquid coming here to heat this water here, which is in a separate circuit, and it produces steam. What you see in yellow here is steam. So yellow is steam, blue is kinda cold water, red is hot water. One thing that doesn't make sense, a hot water at 285 C, and it's still in liquid state. We know that the water starts to boil and transform to steam at 100 C. How comes here at 285 C, almost 3 times the ebullition temperature, almost 3 times the temperature at which the water gets transformed into steam? How much the water is still liquid is because in your house, when you cook your pasta, what is the atmospheric pressure in your house? It's equal to 1013. So the pressure in your house is equal to somehow 1013 bar, right? So that is 1.013 multiplied by 10 power 5 Pascal, because Pascal is the international unit for pressure. That is the pressure in your house. That's why the water that you use to cook your pasta in your house boils and transforms into steam at 100 C, 100 degrees C. This one is not at the same pressure as in your house. It is not at the atmospheric pressure. It is at a pressure way higher, equal to 155 bars. That is why we need something called a pressurizer, which is missing from this drawing. This is what I'm gonna draw here. Which color should I choose? Let's choose green. This is pressurizer here. All right. As any pressurizer, part of it will be liquid, and the other part will be in the gas state, the other part will be steam. This pressurizer is what increase the pressure of water to 155 bars. You don't have 155 bars in your house, otherwise your ears wouldn't be happy. The fact that the pressure is higher, therefore the water does not transform into steam at 100 C anymore. I will make a dedicated video about thermodynamics where I will explain these basic fundamentals of thermodynamics transformation, why water in our house gets transformed into steam at 100 C, and why in this circuit it transforms at a later temperature. That's because the pressure is different. We will see the drawing that explains that, but that's more thermodynamics. There's a separate video about that, which is a super interesting video because I love this topic because it combines many things. It combines electricity, in fact electromechanics. There is tons of automation around it to control all of that stuff. There is nuclear reactions, so we are at the atomic level of, I mean, think of it, there are like 4 forces. The first one is gravity force. This is like when you look at planets, stars, etc. You say, okay, these are like gravity forces. The second one is electromagnetic forces. It happens in many chemical reactions, etc. This one is nuclear force, and there are 2 types of nuclear forces. We'll skip the details for now. The nuclear force happen at a smaller scale, at the nucleus of the atom. You see, like the chemical reaction is like atoms, they will combine each other. There won't be any transformation. I mean, yes, there will be transformation, but the atoms that you see in the beginning of the chemical reaction and the one at the end, they are still the same. The nuclear one is different. The nucleus of the atom, which is the heart of the atom, got split, got a certain transformation. Therefore, the resulting elements are totally different from the atom that has experimented that nuclear reaction. So this is so interesting. You have some atomic science here, you have thermodynamics, you have electricity, you have mechatronics, then you have the transport of electricity, etc., with accounting for the storm, the snow, etc. You see the distance between these cables. It's not random, because if I'm in Switzerland where it can get snowy, I need to account for the fact that for a certain number of months a year there will be a thick layer of snow around these cables. Therefore the distance between the cables need to be increased, otherwise I'm gonna create an electric arc. But if these cables are in the United Arab Emirates, as long as our planet is healthy, I don't expect snow in the United Arab Emirates. Therefore the distance between these cables can be reduced, and that, okay, why it is good to reduce the distance? If you want to keep this distance large, well, the design of this tower will be larger, it will be more expensive. These thinny details, because think of how many electric tower you will have on 400 or 500 kilometers. A lot of them. If we say that between each tower there is, let's say, I'm just throwing a number, 1 kilometer between each two towers, then in this case you will have 500 towers. If you reduce the distance between these three support, then you reduce the cost. Every single detail here matter. That is why we will continue the details here, because this where it gets interesting about the nuclear safety. There is what we call the reactor building, because these things are not all put together in the same room, and there is a reason for it. Anything that is somehow related to nuclear, we will put it in a separate building. So definitely this one. So this is the building that I'm drawing here, okay? So this one will enclose the nuclear reactor for sure, the pressurizer certain, since the nuclear reactor primary circuit, because this one is what we call the primary circuit. This one that you see here is what we call the secondary circuit. So since these two are somehow related, kind of interconnected here, my building needs to enclose also the steam generator. So my building will stop here. All right, so of course the building is straight, has a straight wall, but you got the idea. So this is what we call the reactor building. This one will be called the machine building. One last piece that is missing. We found our source of energy, our source of heat. It's coming from the nuclear reactor. We boiled water into steam. We turned the turbine. The turbine is mechanically connected to the generator, since the generator has a rotor, and the rotor is not made of permanent magnets. This is not your Tesla car. The rotor is made of, there is a winding around the rotor. The winding is supplied separately. That winding creates a fixed flux. But we know an equation called Lenz's Faraday law that says the only way to produce electricity, the only way to produce voltage, is to have a variation of magnetic flux. But I just said that the rotor has a winding that creates a fixed magnetic flux. What makes it variating in time is because the rotor is mechanically connected to the turbine when the turbine turns. Therefore, that flux that was created fixed will be turning, like the way the stator of the generator will see that flux, it will see it as a variating flux, a rotating flux. Why? Because the turbine is rotating connected to the rotor, since the stator will see a variating flux or a magnetic flux that varies in time. The stator has no choice but to create to us a beautiful electric voltage, and that is exactly what we need from the generator. The output of the generator, if I'm not mistaken, is at 15 kilovolt. So the output here is in three phases, of course. There will be a dedicated video about the electric part of this whole story, because this whole story that you see here, nuclear reaction, making it safe as possible, the safest thing on earth that we have is this one, making all of that stuff as safe as possible. This whole story, we do it so that at the end we can produce electricity that we can transport and send to the houses. So therefore here we need to produce electricity. It's a three-phase machine. I will do a dedicated video about it. It's going to be called electric generation, or the electric aspects of nuclear power. Here we have three phases going out like this. These three phases will go to a transformer like this. This is a step-up transformer. It will elevate the voltage from 15K that we have here, 15 kilovolt. It will elevate it to the level at which we will transport that electricity. In this case, it's 400 kilovolt. This is the missing part that we had. Here we go. Now that you have the bigger picture, what's missing? Not that much. This is your house. Electricity is coming through a series of electric towers, transformers in the between, because the level of voltage at your house is 230 volt 50 hertz, but the level of voltage at the output of the power plant is absolutely not 230, is around 15 kV 15, and the level of transport of electricity can go up to 400,000 volts. The frequency is exactly the same. The frequency does not change from the power plant till your house, in theory, because there is absolutely no inverter in the middle that will modify that frequency. We don't need that. You ask at 50 hertz in your house, then the power plant will produce an electricity that is at 50 hertz. You get it from here, from the power plant. You have the generator that produces electricity. The turbine, because someone needs to turn the generator, the turbine will do the job. and the steam coming at a certain speed that will rotate that turbine, gets transformed into water. The water comes here to the steam generator. Someone needs to heat that steam generator because the steam generator does not generate steam on its own. That source of hot, the source of heat comes from someone. That someone, in this case, since we are in Ukraine, since we are talking about nuclear reactor, that someone is a nuclear reactor, and it happens by doing the nuclear reaction at the atomic level. We are talking about the uranium 235, but hold your horses, there will be a dedicated video for that, just for the nuclear reaction. Not only that, there will be a dedicated video for thermodynamics to understand how water got transformed into steam, but also dedicated video for electric production, how we go from a mechanical power, a turbine that is rotating, which has absolutely no electric property, and then we produce electricity. We'll dive a little bit more into the detail of the electric generators. So expect from me video number 1, this one, video number 2, nuclear reaction, the atomic fission, video number 3, thermodynamics, video number 4, electric or electricity production, video number 5, that's going to be the bonus, it's a secret. I will tell you in due time what video number 5 is about, and I swear you will love it, because what you will see in video number 5 has blown me away. One last thing missing before I let you go. Here, the steam gets transformed into water. It doesn't happen alone. There is something that we call the condenser. So the condenser is like this, has bars that have water circulating in them, right? So this is condenser, sorry. And condenser, sorry for my pronunciation. Water is in the condenser, right? That water is fresh, because if you want this steam to become colder, you gotta bring a fresh source of water. 2 ways to do it. You can either take it directly from the river. This is the river is here. It's not a coincidence that we build power plants near rivers or seas. That in some case creates problem to us. In the case of Fukushima, because it was near sea, okay, there was an earthquake, but the proximity to the sea didn't help neither. So we'll take it from the river, because very often near power plants we have a source of fresh water. So this one will come here. This will be a circuit that will come to the river. Of course, there will be pumps, because you want that, the force to take water from the river, bring it to this condenser circuit that you see here, has this cooling pipes here, okay? The other option is that you have a cooling tower. You see, sometimes you see on the picture that a nuclear power plant is kind of releasing like some vapor, like some steam. That's not CO2. In fact, the nuclear reaction does not release any CO2. What is that CO2? I didn't burn anything. The source of my heat is by splitting the atom of uranium. The fact that the atom split, it releases energy. Why? That's what we will see in the next video. But long story short, I don't release any CO2. The steam that you see on these cooling towers is simply because the water coming here will come a little bit warmer at contact with fresh air, then it releases that steam. So that is option number 2. But the most common one is of course the river. But now because the water is getting warmer, the water of the rivers, of the seas, therefore this that we used to call a fresh source of water, it's not going to be fresh anymore, or it's going to be less fresh. So therefore I assume that the future nuclear power plant will have more and more a cooling towers. But in this case, just for the simplicity of the drone, as because I don't have any more space, we'll assume that the condenser takes its fresh source of water from the river. Since I'm in Kyiv, the river that you see behind me is called the Dnieper River. Let's call this one Dnieper. Can I make a confession to you guys? I don't feel my hands. I didn't expect Ukraine to be that cold in October, because we are even not at the end of October. We are on October 25, and it's so cold I don't feel my hands anymore. Therefore I gotta leave you. I gotta go to my favorite cafe, which is called the Blue Cup Coffee, with my favorite waitress named Tatiana. I need my masala tea and my 4 bruschettas. This has been said, my friends. I thank you very much for watching this video. I hope that you got a first good taste of what nuclear reaction and nuclear electricity looks like. I'll see you in the next video, which is going to be about the nuclear fission, or the nuclear reaction that happens in the nuclear core, which creates that source of heat that starts the entire story. Thank you very much. Do widzenia.